Hello once again, class, and welcome to another mock lecture. Today we're going to be talking about a game-changing theorem. A theorem so big that it's going to change the way that you see mathematics as it is. And it's called the fundamental theorem of algebra. So let's get to it. The theorem says that a polynomial f of x with degree n greater than or equal to 1 has at least one complex zero. That's actually it. That's the entire theorem. Now, to refresh your memory, a complex number is something that's of the form a plus bi, where the a is called the real part of a complex number and the bi is called the imaginary part of a complex number. Now, you might be wondering, that's impossible. Think about something like x squared minus 3x minus 40, right? How does that have a complex number as one of its zeros? Well, yeah, let's look at that one. X squared minus 3x minus 40. It breaks up into x minus 8 and x plus 5. Both of those are the factors of x squared minus 3x minus 40. And so its zeros are negative 5 and 8, which are complex numbers, right? Negative 5 plus 0i and 8 plus 0i. They just don't have an imaginary part, but they're definitely complex numbers. Now, there's three corollaries that we're going to talk about for this theorem. I just realized I forgot an L in my title. Oh well, that's going to be there for a long time, so get used to it. The first corollary says that every polynomial can be factored using complex numbers. Here's a proof of that corollary. I'm not going to go through this whole thing. Feel free to pause the video and take a look at this. This is my proof outline for what's going on here. But basically, I just want to point out that in this proof, I started with this. I let f of x be a polynomial with its degree n greater than or equal to 1. By the fundamental theorem of algebra, we know that there exists, remember the backwards e means there exists, a complex zero C1. So I came up with a divisor based on the factor theorem, a quotient, again, based on the division algorithm, and then that quotient either is degree 0 and we're done, or it has a degree that's greater than or equal to 1, which would mean that there's a complex zero. And I just kind of repeat that process. So I start with this claim, and I end with the complete factored form of a polynomial. At some point, the quotient that you end up getting is going to be just some real number, right? And that's going to be your leading coefficient. The logic for this proof just kind of goes until you hit your quotient having a degree of 0. In fact, you could probably prove this thing with induction, but in any case, I started with f of x just being a polynomial with a degree greater than or equal to 1, and I ended with the complete factored form. The second corollary says that a polynomial of degree n has at most n distinct zeros, and if there's any repeated zeros, then in totality there'd be n of them. So let's look at an example of that. All right, example number 1. Assume that the zeros for the following 7th degree polynomial are distinct, and determine the number of imaginary and real zeros. Now for this one, based on the shape of the graph, it doesn't look like there's any repeated zeros, right? There's no multiplicity behavior going on at the x-intercepts. So let's just first count the x-intercepts, and that'll tell us the number of real zeros. Looks like there's 5 of them. Because we know the polynomial is degree 7, there's got to be 7 distinct zeros. 5 of them are real, so 7 minus 5 of them must be imaginary, so 2 of the zeros here must be imaginary. We just can't see them, because they don't correlate to x-intercepts. Right, here's another one. Assume the zeros for the following 10th degree polynomial are distinct. Determine the number of imaginary and real zeros. Again, the real zeros is always the one that's easy to find. You just count the x-intercepts. There's 4 of them. Because 4 of the 10 distinct zeros are real, that means 6 have to be imaginary, and we know that because when you add them together, you get the degree, right, which is a 10. Now, if we wanted to write this in its complete factored form, the real zero parts are easy, right? You've got your leading coefficient times x minus whatever those x-intercepts are supposed to be. But you might ask, how are you supposed to write an imaginary factor? How does an imaginary zero correlate to being a factor? Well, let's look at that, right? Example 3 says, write a polynomial, we're going to call it k of x, with degree 3 and leading coefficient 24, and it's got zeros 2, 3i, and negative 3i. Well, here's the complete factored form. K of x is equal to a, some leading coefficient, which we actually know is 24, so we can actually put that in right away, times x minus the first 0, times x minus the second 0, times x minus the third 0. And the cool thing is we're not going to treat this any differently than we were before. So we've got x minus 2, because 2 is a 0, x minus 2 is a factor. x minus 3i, because 3i is a 0, so x minus 3i is a factor, and then x minus negative 3i will be the last factor, which we could actually make x plus 3i, which may be a cause for concern for you, right? We know that polynomials are supposed to have real number coefficients, and when you see factors that involve some imaginary numbers, you might start thinking, well, now hold on a second. After we do the distribution of all this stuff, isn't it possible that we end up with imaginary coefficients, in which case that's not a polynomial? And that's a really good thought, right? As a student, if you're thinking that, that's really intuitive, because yeah, that would be a problem. But let's actually check this out. If you multiply x minus 3i with x plus 3i, I'm going to use the box method, but FOIL method will work just fine. As I fill this thing out, I get x squared from the x times x, negative 3xi from x times negative 3i, and positive 3xi from x times positive 3i. So those cancel. Those are like terms, and they cancel. And the last box is the one that's the main concern, right? Negative 3i times 3i is negative 9 times I squared. But I squared, remember, is negative 1. I is defined to be the square root of negative 1, and so if you're going to square both sides of that, the square root and the square cancel, so I squared just gives you negative 1. Which means that that box in the bottom right is actually just the number 9. So we just get x squared plus 9 from this multiplication. At this point we could stop, because now the worry of us getting an imaginary coefficient is just completely gone. But just to finish off the problem, I went ahead and I did the distribution. Although I didn't show it, so you're just going to have to believe me. But this is what we would get, right? This cubic polynomial has the zeros 2, 3i, and negative 3i, and it's a polynomial. It doesn't have any imaginary coefficients. So you might notice that in the last 3 examples that we did, all of them had an even number of imaginary zeros. The first one had, I think, 2. The second one had 6. And this one also has 2, right? Imaginary zeros. And actually, it turns out that that's not a coincidence. This is actually the third corollary to the fundamental theorem of algebra, which actually has a name. It's called the complex conjugate zeros theorem. By the way, and I didn't mention this, but this corollary also kind of has a name. It's called the number of zeros theorem. I kind of skipped over that, but that's okay. We can call it the second corollary to the FTA as well. But anyway, the complex conjugate zeros theorem says that if a plus bi is a 0 of some polynomial f of x, then a minus bi is also going to be a 0 for that. So for example number 4, let's say we want to completely factor a quintic polynomial, right? Quintic. Notice I've only given us 3 zeros here, but we know it's quintic. And we also know that it's got a leading coefficient of 7. So there's a couple ways that you could tackle this. The first is you could completely factor given what you already have, which is totally fine. Notice that what I did, when I'm writing factors, it's always x minus whatever the factor is. So in this case, I just put that whole factor in parentheses, right? Because it's x minus that factor. Or rather, I should say 0. It's x minus that 0 is the factor. It's x minus whatever the 0 is. But we know there's going to be 2 more. Right? It's a quintic polynomial. So we know there has to be 5 zeros in totality. That's the number of zeros theorem. One of them is real, and it actually is going to turn out to be that 4 of them are imaginary. Well, if you use the complex conjugate zeros theorem, we also know that negative 5i should be on this list, because that's the conjugate of 5i. We also know that 2 minus 3i should be a 0, because that's the conjugate of 2 plus 3i. So we should write those in these spots here, right? X minus negative 5i, which is just x plus 5i, and x minus the conjugate of 2 plus 3i, which is 2 minus 3i. So that goes in there as well. Okay, now there's 2 things that I want to mention at this stage. The first one is about a common mistake. And this is the common mistake. And you'll have to notice that the sign that I changed using this common mistake is the one that's right after the x. Right? That happens here, you'll notice, because you might point to this and say, well, look, it's the thing right after x that changed here. Well, this 0 is 0 plus 5i, the conjugate of which is 0 minus 5i. So when I go to write this out as a factor, you'll have x minus 0 plus 5i, and then the other one would be x minus 0 minus 5i. But the 0 here is not doing anything. So all I did is I distributed I really didn't even distribute because the 0 is not doing anything. I just kind of applied the negative to this 5i, and that gave me x minus 5i and x plus 5i from here, because the negative times a negative would be a positive. So when there's no real part to the complex number, then okay, the sign right after the x is the one that changes. But when you have a full complex number with a non-zero real part and a non-zero imaginary part, it's the sign between those real and imaginary parts. That's what is changing. So it's not these, right? These don't change, right? Look, if you look at this, that is not the same as this one and this one, because both of them were, up here. Both of those are minus, right? They're both minus right here. So these are the signs that actually change. The sign between the real and the imaginary part. But it's always going to be x minus your 0, right? Unless in the rare case you have no real part to the complex number. Okay, I hope that makes sense. The second thing I want to mention is, you might point to, and this is not a good example because 0, doesn't have a positive and negative value. But let's say that I had, instead of 0, maybe my 0 was 6, right? So instead of this, I would have x minus 6 right there. That's a terrible x minus 6, but hopefully that makes sense. Why is x plus 6 not also a factor? I just went over how whole numbers actually are complex numbers, right? You can write like 3, for example, as 3 plus 0i. Well, the conjugate of that, though, is 3 minus 0i. But those are the same, and so there actually is no conjugate to whole numbers. There's no complex conjugate to the number 4. Something can't be its own conjugate. That's not the definition of what a conjugate is. So that's the reason why we don't have, like, x minus 4 and x plus 4 always showing up, or x minus 3 and x plus 3 always showing up. But why we would have x minus 5i and x plus 5i show up, always in pairs like that. So the complex conjugate zeros theorem is actually good, because whenever you multiply complex conjugates together, that thing happens where we were looking at x minus 3i and x plus 3i, where the imaginary parts cancel out and you end up with just getting whole coefficients. All right, example number 5. Let's say that we want to completely factor this cubic function and we are given nothing about it, right? We don't know anything about this thing. And typically when you know nothing about it, you want to try to find at least one 0, especially when it's cubic, because if you can find at least one real 0, then you can use the synthetic division to divide through, get a quadratic, and then from there you can get your quadratic formula stuff going, or factor traditionally, whatever it may be. But we need a 0 here, okay? You can use stuff like rational zeros test, which I have not done a video on. I may do it in the future, but that is an option here. Or you could graph it. I decided to just graph it. And if you graph it, you're going to find that there's only one real 0 for this thing, which makes sense, right? Imaginary zeros always come in pairs, so you can't have all 3 of the zeros be imaginary, right? A cubic function is going to intersect the x-axis at once, somewhere. In fact, any odd degree polynomial is always going to intersect the x-axis at least one time, because its end behavior is opposite, right? It's either rising to the left and falling to the right, or falling to the left and rising to the right. In any case, I digress. Let's figure out what is that 0. Okay, so I zoomed in on Desmos and I found that this decimal is the 0, and that decimal is actually the fraction 2/7. Okay, so this function has a real 0 at 2/7. We don't know what the other 2 are, though. I assume they're imaginary because they don't show up on the graph. They're not x-intercepts. So let's do synthetic division with 2/7. Okay, so I got my 2/7 in the box because that's the 0. My coefficients for the function are what is listed here. And then I'm dropping down the 7 to get started. 7 times 2/7 is 2, which when you add to 5 gives us 7, which again times 2/7 is 2, add to 12 gives us 14. 14 times 2/7 is positive 4, which when you subtract away 4 from that, you get 0. And we should expect that, right? We knew there should be a remainder of 0 because 2/7 is a 0. That is the remainder theorem. So far we've partially factored r of x into x minus 2/7 from the 0 that we already found, and then now this quotient, 7x squared plus 7x plus 14, for which all of them have a 7 in common, so I pulled out a 7 and I was left with this as the quotient piece. Now there are no two factors of 2 that add to be 1. So I know almost immediately this is a quadratic formula situation. We just need to find zeros. Remember, factoring is just find your zeros, and then it's x minus those zeros become the factor. So to do that, in this case, I had to use a quadratic formula, but I very quickly found my two zeros. They are -1 plus I root 7 over 2 and -1 minus I root 7 over 2. So when I go to factor this thing, I'll have 7 times x minus 2/7 times x minus -1 plus I root 7 over 2 times x minus -1 minus I root 7 over 2. So it looks like this. Right? So again, this sign doesn't change. It's always x minus. It's this one, right? That's changing. But then that's it, right? That's the complete factored form of this thing. We'll go ahead and stop there. I'll do another video, maybe kind of putting together all of the different types of factoring strategies that we've accumulated kind of at this point. So stay tuned for that. But this one just about the fundamental theorem of algebra, the fact that you can factor anything. Right? Every time you've heard before, oh, you can't factor this polynomial because there's no two factors of something that add to be the middle number, right? That turns out it was false, right? You can factor anything as long as you consider complex zeros. So hopefully you guys learned something. If you have any questions, leave a comment below or shoot me an email. Thanks a ton for watching, and I'll see you in the next one.